Hey everyone, this is the fourth lesson in this trigonometric functions unit. We're going to look at both translations and stretches on these sine and cosine functions. Just like any other function, when we talk about vertical translations always show up as an addition or subtraction after the actual parent function. So it's outside of the function, it's just a simple addition after at the end. So the general form for these vertical translations for sine is y equals sine x plus c. For cosine, y equals cosine x plus c. We're going to look at a couple cos examples since we did only sine in our original graphing. Let's look at cos x plus 2 and cos x minus 3. Probably should put an x in there. And as we're used to, these vertical transformations, they always happen the way we think we would. So if we're adding 2, this is telling us shift up by 2. Minus 3 is telling us we're shifting down towards the negatives by 3. So first off, we need to look at our parent function, our y equals cosine of x. So cos of x at cos of 0 is 1. And after that, it comes back down to our axis of symmetry. So in this case, 0 for the parent function, down to -1, back up to 0, back up to 1. And it will repeat this over and over again. Now if we shift everything up by 2 of this parent function, we're going to start at 3. Our axis, when we drop 1, is now going to be at 2. Our axis got shifted up 2 as well. So our axis is y equals 2. We go 1 below, back to our axis of symmetry, then back to our maximum value 1 above. So that is our y equals cosine of x plus 2. Cosine of x minus 3, everything's getting shifted down by 3. So our axis of symmetry now is going to be at y equals -3. Our point, our y-intercept that was at 1 gets shifted down 3 to -2. Our next point is on the axis. Our minimum amplitude's 1 again. Our amplitude stays the same, so we go 1 below the axis, or 3 below our original point, back to our axis, back to our maximum value. So we get the same looking shape, just everything's shifted down by 3 units. That is y equals cos of x minus 3. So this c value that's showing up in our equation, c causes a vertical translation So vertical, we're talking about up and down by c units. Whatever c is, that's how far we're moving up or down. So let's look at what's going to change here. Our period stays the same. Our equation of our axis changes. That's getting shifted up or down. Our amplitude Amplitude here is 1, amplitude here is 1, amplitude here is 1, amplitude's all staying the same. X-intercepts are changing. This function has no x-intercepts. This function has no x-intercepts. Our original function did have x-intercepts. So those can change, as well as our y-intercepts. Domain stays the same. It's all real values for sine and cosine functions, and no amount of shifting around is going to change that. But our range changes. We have new minimum and maximum values. So all of those things change. So if we're asked for those characteristics, we need to be aware that that might change. Now we're going to look at horizontal translations. And again, just like any other function, these horizontal shifts or horizontal translations, they're happening now in the function. It's an addition or subtraction directly to x. So sine of x minus h or cosine of x minus h is how we show this horizontal translation. So we're going to look at two examples again. This time we'll do sine since we just did cos. So we'll do sine of x plus pi over 6. And we'll do sine of x minus 2 pi over 3. And maybe let's give us a little more room to operate here. That'll be 3 pi. So split our x-axis. Each pi is 6 units, so each individual square is going to be a pi over 6. If we draw our original sine, we cross through right at 0. At pi over 2, we get to the maximum value. We come back at pi to our axis of symmetry. Minimum value at 3 pi over 4, and at 2 pi, we're back to 0. And so that would repeat. And we get this nice rounded curve oscillating back and forth. This is our parent function, our sine of x. Now this function here, remember our plus when we're talking about horizontal translations, this is moving towards the negative. So we're shifting left by pi over 6. Because each block was pi over 6, we're shifting left one of these units each time. So every single point, the new point is going to be one unit pi over 6 to the left. And so that is going to give us the same looking curve, just occurring slightly to the left every single time. So that is our sine of x plus pi over 6. So everything's shifted over to the left 1 unit. And when we have a negative, that's telling us we're shifting positive. We're shifting to the right 2 pi over 3. We're shifting right 2 pi over 3. So 2 pi is 12 units. So a third of that, we're dividing by 3. We need to shift to the right 4 units, 4 of these pi over 6s. So our original function here, if we go over 1, 2, 3, 4, we go over 2 pi over 3, we end up here. We go over, again, 2 pi over 3, we end up here. Again, we're moving over pi over 2 to get to our maximum. We're going to move over pi over 2 to get back to our axis. pi over 2 to get to our minimum, pi over 2 to get back to our axis of symmetry, and one last time we're going to end up here. And we can also work backwards. So pi over 2 to the left would bring us back to our axis of symmetry. Oh, we already have that point. I went too far over. Back to our axis of symmetry. Pi over 2 to the left would bring us to our minimum here. So we would get a shape that looks approximately like this. And this is going to be our function sine of x minus 2 pi over 3. So as we can see, I'd already written in this from before. When we were shifting left pi over 6, each unit was pi over 6. We shift 1 unit to the left. Or we shifted 4 units to the right for 2 pi over 3. 4 pi over 6s is the same as moving over 2 pi over 3 if we simplify that fraction. So that is our horizontal translations. And so we can wrap this up by saying our h value causes a horizontal translation. Horizontal is going to be left or right. And specifically when we're talking about sine and cosine functions and other cyclical functions, this shift is called a phase shift. We're still cycling back and forth. We're just shifting that cycle. So that's translations of sine and cosine. We'll look at stretches of sine and cosine now. So we'll start off with vertical stretches of our sine and our cosine. And those are going to show up same as the exponential and logarithmic functions, same as any functions that you've talked about over the past couple of years. It's always a multiplication outside of our function. So we have our parent function, and the whole function is going to get multiplied by some value. So we'll start off looking at our standard sine of x, which has an amplitude of 1 and a period of 2 pi. That's standard. Y equals sine of x, starts at 0, goes up to 1, back to 0, down to -1, back to 0. Because the period was 2 pi, that's happening each of those key points is pi over 2 away from each other. So that is our y equals sine of x, our standard function. Y equals sine of x. What happens if we look at y equals 1/2 sine of x? 1/2, if we remember from our previous units, that's going to compress all of our y values. So we have a vertical compression by 1/2. That distance of 1 from our max to our axis, now we're only going half as far, but our period, because that's a horizontal measure, is going to stay the same. That's still going to be 2 pi. So all of our points are multiplied by 1/2. 0 times 1/2, we stay at 0. -1 times 1/2, we'll end up down here. 0 times 1/2, we end up at 0 again. So we get that same maximum and minimum values at the same points, but it's slightly shrunken. It's slightly compressed. So this is our function y equals 1/2 of sine x. What happens if we have a vertical stretch? So we have a number bigger than 1 multiplied. So vertical stretch by a factor of 3. Our amplitude, now all our values are 3 times as far. So the furthest away we get from our axis is 3 units. Our period stays the same because we haven't done anything to our horizontal points. So we're still going to have a cycle every 2 pi. 0 times 3 is 0. 1 times 3 is 3. So we end up all the way up at 3, back down to 0, all the way down to -3, and back to 0. So we get this dramatic curve going from -3 to 3. That is our y equals 3 sine of x. For vertical stretch, same shape, same x-intercepts, slightly different shape just because it's stretched so much. But we're still using our same 5 key points to create one period. And let's throw in a function with a vertical reflection, so a reflection over the y-axis for good measure. So -2, all of our y values get multiplied by -2. The negative doesn't affect our amplitude, but our new amplitude is going to be 2. Our minimum and maximum are both 2 units away from our axis. And our period again stays the same, so it's still going to be 2 pi. -2 times 0 is 0. -2 times 1 is -2. -2 times 0 is 0. -2 times -1, we're at +2, and back down to 0. So we get this same sinusoidal, the same shape, just we're going down to start. And this is our y equals -2 sine x. So what can we say about the a value? The a value is causing a vertical stretch. Could be an expansion, could be a compression, and changes our amplitude. So if a, the absolute value of a is greater than 1, doesn't matter if it's positive or negative, but the actual value, how far away from 0 we are, then we're expanding vertically by a. If that absolute value is less than 1, we're compressed vertically. And compressions, we can either say we're compressed by we're compressed by a half. You can also say you're compressed by 2. Generally, we prefer to use the fraction because it's a little more self-explanatory. And if the actual value of A is ever less than 0, doesn't matter if the absolute value is greater than 1, that is a reflection across the x-axis. Lastly, we're going to look at horizontal stretches and compressions. So horizontal stretches and compressions, again, always happen inside. Horizontal, it's inside the function, so it's directly affecting our variable. So it's a direct multiplication of theta or x, depending on how we write it. We'll look at cosine theta this time. So y equals cosine theta. Our y-intercept at x equals 0 or theta equals 0. Our function's at 1. Then halfway to pi, we hit our axis. At pi, we're at -1. 3 pi over 2, we're back at the axis of symmetry. And then we hit our maximum value. And it'll keep oscillating under that pattern in both directions. So that is our cosine of theta. Our root function. Here our period is 2 pi. It takes 2 pi to complete one cycle. And our amplitude is 1. Let's take a look at y equals cosine of 3 theta. So this is a horizontal compression by 1 over 3. So our period, because period's dealing with our x values, is being shrunk. It's now a third of what it was. So our period's going to be 2 pi over 3. And our amplitude's y values, so amplitude stays the same. So everything's going to be a third the distance from the y-axis. So it's still going to go through this point here, but now this point that was 1, 2, 3 units away, 3 pi over 6 or pi over 2 away, now is going to be at pi over 6. This that was 6 units away, 6 pi over 6 or pi units away, now is going to be pi over 3, or 2 of these pi over 6. 9 units away, now is going to be 3 units away. 12 units away is now going to be 4 units away. So you can think of it either in terms of what these boxes are worth. Each box is pi over 6, or how many boxes away we are. Either way will work, but we're going to get this much narrower shape here. And it's going to keep repeating over and over again. And that is our y equals cos of 3 theta. Y equals cosine of half theta. Dividing by 2 or multiplying by a half, that's an expansion or a stretch by a factor of 2. We're multiplying all of our x values by 2, so our period's now going to be 4 pi. And our amplitude stays the same because we haven't done anything to our y values. Our amplitude's going to be 1. So for our original function, we're still going through at y equals 1. We're stretching by 2. So instead of pi over 2, we're going to be crossing at pi. This point that was at theta equals pi is now going to be at theta equals 2 pi. And so now instead of every pi over 2, we have that turning point, or that key point. Now every pi. So we're going to go another pi over, we're back at 0. Another pi over, so another 6 units over, we're up at theta equals 1. So we get a much more stretched out looking cosine function. So that is our y equals cosine of a half theta. And we'll also look at a reflection. Y equals cosine of negative theta, period. A reflection, yes, it's going to change all of our points, but our period is still going to be 2 pi. Periods can't be negative. Negatives don't affect them. And our amplitude stays equals 1. All that happens is these points are now reflected across. So this pi gets reflected over to negative pi. Oh, that's the wrong function. I don't have very many colors here, so I apologize. Sorry, the original function was pi over 2. So this is going to be negative pi over 2. Pi is going to be negative pi over here. Negative 3 pi over 2. Negative pi. Sorry, negative 2 pi. And this is going to be our y equals cos of negative theta. Some of you may have realized this cosine of negative theta, this is actually going to follow the exact same path as our original function did anyways. So cosine negative theta is actually the same function as cos of theta. But we'll get into that a little bit later. The d value causes a horizontal stretch and changes the period this time, not the amplitude. Amplitude is vertical, so there's a vertical stretch that changed that. So our period is always going to be 2 pi over that d value. Whatever we have multiplied by our angle in here, that is what we're dividing 2 pi by. If when d is greater than 1, that's a horizontal compression by 1 over d. If that absolute value is less than 1, horizontal stretch by 1 over d. We need the reciprocal again. And no absolute value this time, but if d is less than 0, we have a reflection across the y-axis. So you might be asked to graph some of these combinations of functions. Again, I know that the graphing side of things is going to be somewhat, no pun intended, somewhat sketchy, especially if you're doing it on line paper. Just make sure you're showing those 5 key points. We'll go through an example or two. There's 2 examples that are listed already on the completed note, and then 5 that are not. So I'm going to go through some of these uncompleted examples just to give you a little extra practice. But if you have any questions on those 2 that are completed, let me know. And so we'll start off with y equals 2 cos 4 is out of 5 over 5x. Where we're in between 0 and 2 pi for x. So that means we have a vertical stretch by 2. That 2 right there is telling us we have that vertical stretch. And we also have a horizontal stretch or horizontal expansion by, we need the reciprocal, so by 5 over 4. So what is that going to change? It's asking amplitude. Well, amplitude was affected by vertical stretches. So if our vertical stretch by 2, our amplitude is going to be 2. Period was affected by horizontal stretches. We need to do 2 pi divided by d. So 2 pi divided by 4 over 5, or 2 pi times 5 over 4. We can cancel out a 2 from the top and bottom, and we're going to get 5 pi over 2 as our period. Domain, sine and cosine functions always all real numbers. Our range, our axis isn't moving at all. So our axis stays at 0. Our amplitude is 2. So that means we can go as low as -2 and as high as +2. And this is going to be a very rough sketch. We need 5, period is 5 pi over 2. We can kind of cheat when we're drawing these. If we have no shifts, we know it's a cosine function. We're going to get this general shape of starting at our maximum, axis symmetry, minimum, axis symmetry, maximum. Our period has to be 5 pi over 2. Our maximum was 2. Our minimum is -2. This is 5 pi over 2. This has to be 5 pi over 4. This has to be 5 pi over 8. This would be 15 pi over 8. In your actual sheet, they give you all your x values. So we can't quite use this method, but it's up to you. 5 pi over 2 is labeled, 5 pi over 4 is labeled, 5 pi over 8 is going to be halfway in between here. So right in the middle of pi over 2 and 3 pi over 4. We're still going to get this exact same shape. It'll just look a little bit different on this graph, but overall the same. I will leave these other examples. If you do want me to post any more of the ones I didn't go through, let me know, and I can do it on a scale that mirrors what is on the sheet. But because I don't expect You all have printers. I'm not going to ask you to print off these sheets and graph things on certain scales. It's going to be up to you to create the scales. And when it's up to you, you can use shortcuts like that to really make the scales benefit your drawings. You don't have to use a hard, fast, consistent scale on every single drawing. Here, 3 units is 5 pi over 8. That's completely okay because that makes drawing that a lot easier. So we'll end off there. You'll hear from me again soon. And I hope everything's going well. Let me know, as always, if you have any questions, and talk to you soon. Bye.